So there are a lot of things in this world that they say are easy to learn but difficult to master. Um, Myself, well, sometimes I think that gives the impression of some elite group of upper echelons who will only be the only people able to wield whatever it is for their nefarious means. But I myself learned originally from the Googles and Stack Overflow schools of programming. Um, but these days, I find a real sense of joy and satisfaction from being able to approach a problem from scratch myself and arrive at a working solution. Especially, it's great when you can get just a sheet of paper and a pen out and you can work through the problem by hand and you feel you've got a solution and find that it's actually relatively easy to then express that to the computer. And it's an even better feeling when you can refine that idea into something that really expresses what you're trying to do well to other people in the same language as you expressed it to the computer. So since you're here today, you've probably heard of this thing called APL. And maybe you've seen some examples, maybe you haven't, but maybe you've already started to form some kind of impression. Maybe you've started to experience some relatively strong emotions. I'm not sure. For the next little while, I hope to introduce you to some of the simple, fundamental rules which, quite surprisingly, do enable you to express things in a variety of ways in a variety of different contexts once you get used to them. Although you might obviously be thinking, okay, a language where the core of it is expressed as this notation with symbols, am I going to have to commit to buying another piece of hardware just so I can write over it? Get desperate like this poor soul here? Well, actually, I think this is kind of cool. Actually, you find that learning typing APL is one of the lowest hurdles you'll have on your journey. Really, the benefit and difficulty comes from learning to compose the constructs in different ways in order to solve a variety of problems. I'm not going to lie, I'd say if you had a Playmobil castle like this one on the left, you're going to get quite quickly and easily from 0 to full castle, probably quicker than you would trying to build from plain Lego bricks. You've got these pieces, maybe they're, somewhat large, but they're designed to slot together to build a castle, and that's about it. In this analogy, in contrast with Lego, it might take you longer to build up to a full completed castle, but once you've done so, you'll have a better understanding of the way that these fundamentally simpler pieces compose together, and you'll have more confidence in breaking those structures apart and repurposing them to build something possibly entirely different. Although, again, you say, yeah, that sounds cool, but at the start, it's still quite daunting to be presented with all of these potentially unfamiliar pieces. You're not sure how they slot together, and you're not sure how to begin. Perhaps even you think, well, glyphs are one thing, but actually maybe you could just be nice and give me some keywords. Well, APL actually doesn't prevent you from assigning any of these, assigning these symbols to keywords if you want to. People don't tend to do that. I mean, keywords are definitely useful, but in some sense, there's a bit of there are some limitations. So, as a simple example, you might have learned to become familiar with adding two values with a plus symbol. But when you come to then generalize that, you're doing A plus B. But when you're then generalizing to add together an entire list, that's a sum, and that's a different word. Similarly, I think it was A-level electronics where I started learning about Boolean logic and using the symbols for anding together two predicates. But once you have an entire list of predicates, you're actually asking, are all true? APL symbols are able to generalize in a way that suggests different behaviors so that you can learn some basic rules and then see how those constructs apply in different places in different ways, without having to learn an entire new vocabulary when you want to do something else. And sure, there's like about 80 symbols, and some are used more commonly than others, but to start with, you probably already know some of them. If you've done any type of basic mathematics, operations with numbers, some comparisons which are very common, or perhaps you've seen these symbols which come from formal logic and set theory, you're not necessarily learning everything from scratch. And even those symbols that seem to be unfamiliar at first, they're designed to have a shape that might suggest its meaning a bit. So for example, reversing an array across the vertical axis. Or a transpose, which, at least in the matrix case, is reversing across the diagonal. And perhaps you've got some numbers on a number line and you want to round them up. Or round them down. APL has symbols for these types of common operations. Or you can take yourself back to when you first started to learn to count, or count larger numbers of things, I suppose. 1, 2, 3, 4. And that's the symbol for tally. Yes, it's pointed out that dyadic symbol operators cannot be assigned a name. That's just an unfortunate limitation. I think you can wrap it in a diop, and if you don't know what that means, Stefano's question wasn't for you then. Okay, so say we've gotten through the symbols and we're into this now. How do you actually use this thing? How do they work? The syntax is remarkably simple at the basic case. We have 2 argument infix functions. APL calls them dyadic functions. And you might be familiar with some of these, right, from your life. Multiplication and subtraction. And we have 1 argument prefix functions. APL calls these monadic functions, but they're nothing to do with functional monads. So the prefix version of the hyphen is negation. And so some of the symbols will have 2 function meanings, but often those 2 functions are closely related. So in a sense, this is like a shorthand for 0 minus, right? And you can even contrast this with traditional mathematics and even some programming languages where they've had to define or chosen to define some specified order of operations. You might know this as BODMAS or BIDMAS, or I think PEMDAS in some countries. Basically, do you do the brackets, then the exponentiation, then the multiplication and division, and then addition and subtraction, no matter where they are in the expression? Well, in a language in something like APL, where the core language consists entirely of symbols, how would you choose the precedence in that case? APL makes it all egalitarian and says we're going to have everything be dyadic infix functions or monadic prefix functions. Even user-defined functions are like this. So here's one you haven't seen before. Iota generates indices or integers. Right, so that's the basic, that's the syntax. But how do we piece this together to form expressions? APL syntax, I think, is nicely described as having short left scope. Functions have short left scope and long right scope. Sometimes this is referred to as right to left precedence or order of execution, but really it means for a given function, your function takes the result of the entire expression to its right as its right argument, and if there is a left argument, it will be the value, the array, immediately to its left. So in this case, there is nothing immediately to the left, so it's monadic. Iota 7 generates the first 7 integers. Oh, I should have mentioned what I'm doing here. Well, we'll see in a second. We can then build on this towards the left, right? So now that we've got the first 7 integers, let's multiply those all by 2. And then let's add minus, so that's all the even numbers. To get from the even numbers to the odd numbers, we can add -1, or add -1. So just to re-emphasize, let's think about how the computer kind of approaches this. We have this expression, and we start from the right. We look for an array value. In this case, it's a literal single number 7. And then APL looks at this symbol. Okay, that's a function. Is it monadic or dyadic? Well, it looks to the left and it sees there's no array value before the next function. So it's just a single argument to its right. So it evaluates that. There's our first 7 integers. Now we look at the multiplication. We know we have the result of everything to its right as the right argument. We look to the left, we see a single array value before the next function. So then that's dyadic. Multiply 2 times each of the numbers in our list. And the same with the plus and the -1. So yeah, so that's how you generate a sequence of odd numbers. Great. Well, now let's move it up half a gear, I suppose, and look at our first taste of the generality offered by what in APL are called operators. They're a kind of one level higher order function. Let's look at how to sum up a list. Now, if we have a literal list, it's easy to see we could just insert pluses in between each of our elements here. And if we look at this in terms of the order of execution, from the right we have a literal 6. We see the plus. We see the -4 to its left, so that's dyadically applied. 6 plus -4 is 2. And then it's plus, and then the 8, so 8 plus 2 is 10. 10 plus 5 is 15. The sum of our list is 17. We can take this principle and apply it to another kind of dyadic function. So let's take the maximum function. Our literal 6, which is greater, -4 or 6? Or 6 is greater. 8 is greater than 6. 8 is greater than 5. 8 is the maximum value in our list. I suppose you can already see a problem, right? This is a relatively small list. If we have lots of data, we're not going to have it literally written out like this. We're either going to have read it from a file or got it from the internet or something, and it's likely to be a variable stored and referred to in a name or by a name. So we can assign this list nums. But once we have it in a name, we can't break it apart to insert pluses, and even if we could, that just would be tedious. So the first operator I'm going to show you is the /, although we've already seen it a bit. And yeah, so these operators basically take a function. Most of them take a single function on the left, and they'll apply that in a particular way. In this case, okay, we've seen the sum. But we can apply this, yeah, to any of our functions. We've seen the max. There's the min. And with the times reduction, that's the product. So yeah, with operators in this way, maybe we've learnt 4 symbols for 4 functions, but we've learnt 1 operator and doubled our money. We're on 8 functions now. And in fact, if you, instead of a /, you use a \, you get all the cumulative versions of these functions for free. So it's basically the same idea, but with the intermediate values. 2 + 5 is 7, 2 + 5 + 8 is 15, etc. Okay, one more operator before we put stuff together into something more. This one's called the outer product. So we're going to start with our list of numbers again, since we're familiar with using those now. This is just one bit of syntax that's slightly different from the rest of the monadic operators, but it does take a single function, in this case the times, and it's going to apply that function between all the combinations of the elements in the left argument and the elements in the right argument. So if we have a single list of numbers, 1, 2, 3, 4, 5, 6, 7, this becomes a multiplication table. So hopefully that's something that you're familiar with. Maybe you get the idea of what's happening here, at least a little bit. But obviously the power is in the generality. It's not just a times table we can make. If I change the function to a plus, then that's an addition table. Maybe it's something so trivial people don't tend to make them, but they can be quite useful, as we'll see in a minute. Or how about a max table? Might not have thought what that would even look like. It doesn't have to just be those types of numeric things. I mean, here's a comparison. An outer product equality turns out to be a neat but relatively inefficient way to generate an identity matrix. But sometimes an outer product comparison is just what you need. Okay, so we've got the idea of the symbols, we've got the basic syntax and how pieces are put together. Now let's try to sort of do something with it. I've got 2 dice, and if I roll them, then that roll will have a value which is the sum of the values of each of the dice, right? So if I roll a 1 and a 4, then the sum is 5. Well, what's the distribution of all the total ways that all of the sums that you can get from rolling 2 dice? Let's take a look at how we do this using the pieces that we've got. So for a single die, the possible throws are the integers 1 to 6. And all the possible sums of rolling 2 dice, well, that's an outer product. That is the addition table from earlier. And we're interested in the distribution of dice throws. But actually, we can already see what the pattern is, or how it behaves, right? It looks like there are 6 ways to roll 7 to get to 7. Oops. Since we just want all the values for right now, we don't want this 2-dimensional structure at the moment, I'm going to ravel out this matrix in row order, so we'll have a single list that goes 2, 3, 4, 5, 6, 7, then 3, 4, 5, 6, 7, 8, then 4, 5, 6, 7, 8, 9. And I do that with the monadic comma. That's the ravel function. So there's all of our possible sums from throwing 2 dice. What are the unique values? So these are the unique possible sums. And to count the ways that you can get them, we can take an outer product between our unique sums and all of our throws. So what does this look like? Here's a relatively large matrix. Maybe it gets a bit dizzying from looking at all those ones and zeros, but it's not that bad. It's simply saying for each of the unique values, so each row is an equality comparison between each of the unique values and all of the possible sums. And a 1 indicates where they're equal, right? So you can follow them across 9 and 9. So now we have this matrix, which is like an occurrence count for all the different sums that we could throw with 2 dice. So how do we add up the occurrences? Well, we can just use a sum from before. Plus slash is a row-wise sum. So we're going to add up along each of the rows. One caveat, just in terms of the display, is we had a 2-dimensional structure before, this matrix, the Boolean matrix. Reduction, the operator, actually reduces the dimensionality of an array by 1. So we go from having our 2-dimensional matrix to a 1-dimensional vector, is what we call it. It's basically a list, so it will display horizontally. So that's basically it, but for larger sets of data, it can be unwieldy to just stare at a list of numbers. So why don't we try visualizing it a bit? How can we do this? Again, just using the tools that we've basically already got, although I'll be adding one more. So for a histogram, the highest count is the maximum of our counts. And all the unique values happen to be the indices up to the counts. We could have also produced this with unique and sorting, but this is just a bit of a neat way to do it. And then to get a nice display of what the counts look like, we can do an outer product comparison. This is kind of neat, but I think it could be nicer if we visualized it a bit more graphically. So here's a bit of an aside. One of the neat things in APL you might have seen in programming before, indexing into an array using square brackets. So the 4th character in this character vector is a C. But in APL we can index into arrays with arrays all at once. And even nicer is even if we have a higher dimensional array or array with different shapes, so here's a 2x3 matrix of indices, the result of an indexing expression has the same shape as the shape of the indices. Well, has the same shape as the indices. So we can exploit this to make this a bit prettier. Indexing in APL starts from 1 by default, but that's easily accounted for. So now we have a matrix of indices, but we only have 2 values that we want. So we're going to create a 2-element vector of characters. One is just a space character, and the other is a jot. which is the same jot that comes from the jot dot in our outer product, but we could choose any symbol. And now the 1s are going to essentially be replaced by spaces and the 2s with jots. So that's a prettier visualization, I think, and maybe we can drive it home by tacking on some axis labels by just catenating our unique values. Oops, sorry, I'll let you see that for a second. Before finally, we can bring all of our pieces together. This is everything we've done with just a few functions and a couple of operators. We've managed to build the distribution of these dice throws. And if we want to generalize this from, I guess, just not 6-sided dice, but any integer-sided dice, then we can use an argument omega and wrap this as a function. And we can do whatever our imagination dreams of, like the mythical 3-sided die.